Hey everyone, we're Ballers Inc. and we're excited to present to you our game, Balhalla, Battlefield of Glory.
We created our own version of a .io game, Balhalla. From this, we took inspiration from Slither.io, Agar.io, and Diep.io. So, what was our motivation? We wanted to create a Viking theme IO game of dodgeball. When a player dies, they'll turn to a ghost where they can go around and nudge the ball, interacting with the game post-death. Our game puts a greater emphasis on performance and thus accessibility on lower-end devices. We want to have a big focus on fun gameplay over just fancy graphics.
Now that you know what Valhalla is, we'll be going into the live demo, our architecture and design choices, the implementation, testing, and CI/CD pipeline, and of course our reflections at the very end. For our live demo, you're welcome to join us and play the game yourself with the link in the chat. For now, I'm going to quickly go over what our game entails. First, we have our use case diagram, which shows us that you're able to log in, register, visit the store, play the game, and access the leaderboard, which are our primary functions. Our activity diagram shows the process of authentication and the game activity, and the exchanges between different systems. Our class diagram shows us the specific classes and the attributes and the functions that each of them hold. We also have the sequence diagram that shows the messages exchanged between each of our different systems and functions and classes. And finally, the state diagram, which reveals the different game states that we have, which of course defines our game behavior and is very important. Now I'll hand it off to the rest of my team for the actual live demo.
Next, we will talk about our architecture and design choices at a high level. Our two main focuses are performance and scalability. Since this is an online multiplayer game, we want to ensure that we can handle as many people as possible without introducing lag for any users. We achieve this through our choices in handling user controls, game logic, and data storage. Our application landscape uses a three-tier architecture where our front end uses Three.js and our backend uses Postgres, and they both communicate to our Vite and Node server in the middle. Our client sees our React view, which is inherited from an abstract view. Any actions made by our client propagate to the abstract presenter, which is then sent to our concrete Three.js presenter. The presenter updates our server, and our server returns the necessary game logic, which is then forwarded to our view to be updated. Note that we did not use a specific application structure pattern within components, so we did not include it here.
The first of the design patterns we decided to use is the mediator pattern. We have each client's display and controls communicate to their corresponding WebSocket, and each WebSocket is connected to our central game logic server. This satisfies our functional requirement of syncing up all of our information in one central place in order to prevent game lag and desync. The mediator pattern also helps us with our non-functional requirement of scalability, allowing us to expand bandwidth in our server whenever needed. The second pattern we used is the state pattern. Since our application is a game, we needed to separate out all of the game states into their own components, such as game start, game end, and the lobby state. Our functional requirement of having a working game with proper game mechanics is optimized using the state pattern. And lastly, we utilize the singleton pattern for specific elements that we know only one entity should exist, eliminating any confusion with our WebSockets or clients. This aids in the functional requirement of having a central camera and client ID, which our game logic and WebSockets both need to access.
Hello, my name is Evan, and today I'll be talking about the implementation, testing, and CI/CD process. First, I'll be talking about our implementation choices. We decided for the front end that we would be using Three.js, React, and WebSockets. The reason we decided to use Three.js is because we wanted to have a 3D game, and it provided several advantages over using just plain WebGL. Secondly, we wanted our game to have real-time multiplayer, so we use WebSockets to communicate small amounts of data very quickly between each client. And then third, we decided on using React as a front-end library for our user interface because several of our team members had quite a lot of experience using React, and it was a very simple and robust way to display data. For the backend, we decided on using Node.js as our game server and API endpoints as it unified everything under one programming language. For our database, we decided on using Postgres as a backend because some of our members had experience using it, and our platform as a service and CI/CD provider, Replit, provided it free of charge. Let's get into our testing strategies. First, for our backend testing strategies, we use unit tests to easily test functions such as the database and our API endpoints for things such as authentication. For front-end testing, however, it was a little bit different. Because video games do not have an easy pipeline for unit tests, we decided on procedural testing. These would be things such as ensuring that all clients are synced up, whether it's player movement or balls being thrown. That was the procedural testing we used for the front end. And then for future proofing, we use regression testing for all major changes. For our CI/CD process, we use Replit as our CI/CD builder. Replit is a third-party service. As I said before, it's a platform as a service that handles continuous integration and deployment for Balhalla. Similar to Vercel, anytime a change is merged into the GitHub repository, it would commit that change to Replit, and Replit will automatically rebuild and deploy the most recent copy of the repository straight to our domain.
Hi, I'm presenting the reflection of what we went through and what we learned from the project. So our version of the Scrum process had 2-week sprints. At the end of every week, we had stand-up meetings. At the end of the sprint, we had reviews and retros. We had to notify each other whenever we were blocked so we could all make progress. So member roles. Evan was the tech lead. He handled sockets and game logic. Philip was Scrum Master, so he handled modeling and documentation. I handled the projectile behaviors and ghost behaviors. Ishan was making UIs and the login sign-up front end. Yang handled most of the menus like shop and profile pictures. And Devil handled the developing database, including the login and sign-up fetch. So what we learned, the Scrum process is really good for the work environment, but for students, where we have 2 other classes to handle, it takes up too much time, all those meetings. On top of that, we realized onboarding takes a lot more time than expected because we all needed to be up to date and understand what the vision for the project was before we could actually code. Potential improvements for the future. We would hope to have more complex player movements and behaviors. We also want to provide more items in the shop, and we could also have more tight security for accounts. Okay, and here's the progression of our sprints. As you can see, we had an average of 4 stories per sprint, but we had exponential growth in completion rate because at the beginning, we had to onboard everyone, we had to get synced up in what we wanted to make. And at the beginning, when we had made changes, it was hard to update everyone on what was happening, but we got more synced up as the progress went on.
That was our presentation. Thank you for listening, and please let us know if you have any questions.